Hello viewers, welcome to Math Tech. I am Amit Sharma. Welcome to the lecture series of Abstract Algebra for CSIR NET, GATE, NBHM, TIFR, MSc Mathematics and IIT-JAM exam. This is part 2 of lecture 4. If you haven't seen the part 1 of lecture 4, please go and see. You can find the link in description box. For rest of the viewer, let's start. Isomorphism of infinite and finite cyclic groups. Number 1. If G be an infinite cyclic group, then G is isomorphic to Z. Number 2. If G be a finite cyclic group, then G is isomorphic to Zn. Number 3. If order of G is P, where P is a prime number, then G is isomorphic to Zp. Is Q star a cyclic group? Answer is no. Question number 1. Show that Q star is not a cyclic group. Order of Q star is infinity. Let if possible Q star is a cyclic group. Implies Q star is isomorphic to Z. We know that Q star has elements of order 1, 2 and infinity. Implies Z has elements of order 1, 2 and infinity. But Z has no element of order 2. Implies Q star is not isomorphic to Z. Hence, Q star is not a cyclic group. Similarly, R star and C star are not cyclic groups. Is GLNF, where F is QRC, means infinite field, a cyclic group for each n? Answer is no. Let's check for each n. For n equal to 1, GL1F equal to F star, and F star is not a cyclic group. For n equal to 2, GL2F is non-abelian group, implies non-cyclic group. Result: GLNF is non-cyclic group for each n, where F is an infinite field. Next is GLNZP a cyclic group for each n? Answer is no. Let's check for each n. For n equal to 1, GL1ZP equal to ZP star, which is equal to U of P, and U of P is a cyclic group, implies GL1ZP is a cyclic group. For n equal to 2, GL2ZP is non-abelian group, implies non-cyclic group. Result: for n greater than equal to 2, GLNZP is non-cyclic group, where Zp is a finite field. Next is SLNF a cyclic group for each n? Here F is finite as well as infinite field. Answer is no. Let's check for each n. For n equal to 1, SL1F contain the element 1 only, and the order of 1 is 1, which is equal to order of SL1F, implies SL1F is a cyclic group. For n equal to 2, SL2F is non-abelian group, implies non-cyclic group. Result: for n greater than equal to 2, SLNF is non-cyclic group. Next is uniqueness of the cyclic group of order n. Let n be a positive integer, then the cyclic group G of order n is the only group of order n if and only if we have GCD of n, phi n is 1, where phi denotes the Euler's phi function. Question number 2. This question was asked in NBHM MA MSc exam in 2013 as well as in 2018. Which of the following statements are true? Option A, every group of order 11 is cyclic. Option B, every group of order 111 is cyclic. Option C, every group of order 1111 is cyclic. We know that group of prime order is cyclic, implies option A is true. Now GCD of 111, phi of 111 equal to GCD of 111, 72, which is equal to 3 and which is not equal to 1, implies group of order 111 is not a cyclic group, implies option B is not true. Again, GCD of 1111, phi of 1111 equal to GCD of 1111, 1000, which is equal to 1, implies group of order 1111 is a cyclic group, implies option C is true. Hence options A and C are true. Next is number of non-isomorphic abelian as well as non-abelian groups according to the order of the group. The table shows order of group, number of non-isomorphic group, number of non-isomorphic abelian group, number of non-isomorphic non-abelian group. If the order of group is 1, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and the group is Z1, and there is no non-isomorphic non-abelian group of order 1. If the group has order 2, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and the group is Z2, and there is no non-isomorphic non-abelian group of order 2. If the group has order 3, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and the group is Z3, and there is no non-isomorphic non-abelian group of order 3. Next is, if order of G is less than or equal to 3, then G is always a cyclic group. Next, if group has order 4, then the number of non-isomorphic group and number of non-isomorphic abelian group is 2 and the groups are Z2 and Z2 cross Z2, and there is no non-isomorphic non-abelian group of order 4. If the group has order 5, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and group is Z5, and there is no non-isomorphic non-abelian group of order 5. Next is, if order of G is less than or equal to 5, then G is always an abelian group. Next is, if group has order 6, then there are two non-isomorphic group, one is Z6 and one is S3, out of which one is non-isomorphic abelian group, which is Z6, and one is non-isomorphic non-abelian group, which is S3. If the group has order 7, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and group is Z7, and there is no non-isomorphic non-abelian group of order 7. If the group has order 8, there are 5 non-isomorphic groups, namely Z8, Z2 cross Z4, Z2 cross Z2 cross Z2, D4 and Q4, out of which 3 are non-isomorphic abelian group, which are Z8, Z2 cross Z4, Z2 cross Z2 cross Z2, and 2 are non-isomorphic non-abelian group, which are D4 and Q4. Next is, if group has order 9, then the number of non-isomorphic group and number of non-isomorphic abelian group is 2 and the groups are Z9 and Z3 cross Z3, and there is no non-isomorphic non-abelian group of order 9. Next is, if group has order 10, then there are two non-isomorphic group, Z10 and D5, out of which one is non-isomorphic abelian group, which is Z10, and one is non-isomorphic non-abelian group, which is D5. Next, if group has order 11, then number of non-isomorphic group and number of non-isomorphic abelian group is 1 and the group is Z11, and there is no non-isomorphic non-abelian group of order 11. Next, if group has order 12, there are 5 non-isomorphic groups, namely Z12, Z2 cross Z6, D6, A4 and Q6, which is generated by M, N, out of which 2 are non-isomorphic abelian group, which are Z2 and Z2 cross Z6, and 3 are non-isomorphic non-abelian group, which are D6, A4 and Q6. Next, If group has order 13, then the number of non-isomorphic group and number of non-isomorphic abelian group is 1 and the group is Z13, and there is no non-isomorphic non-abelian group of order 13. Again, if group has order 14, there are two non-isomorphic group, one is Z14, another is D7, out of which one is non-isomorphic abelian group which is Z14 and one is non-isomorphic non-abelian group which is D7. Next is some observations. Number 1, if order of G is P, where P is a prime number, then G is isomorphic to Zp, that is, there exists a unique non-isomorphic group of order P. Number 2, if order of G is P square, where P is a prime number, then G is isomorphic to either Zp square or Zp cross Zp, that is, there exists a two non-isomorphic group of order P square. Number 3, if order of G is PQ, P less than Q and P divides Q minus 1, where P and Q are prime number, then G is isomorphic to either ZPQ or a non-abelian group of order PQ, that is, there exists two non-isomorphic group of order PQ. Number 4, if order of G is PQ, where P less than Q and P does not divide Q minus 1, where P and Q are prime numbers, then G is isomorphic to ZPQ, that is, there exists a unique non-isomorphic group of order PQ. Question number 3. This question was asked in NBHM MA MSc exam in 2008. Which of the following statements are true? Option A, any group of order 15 is abelian. Option B, any group of order 25 is abelian. Option C, any group of order 55 is abelian. Let order of G is 15, which can be written as 3 into 5 with 3 less than 5, and 3 does not divide 5 minus 1, implies G is isomorphic to Z15, which is a cyclic group, implies an abelian group. Therefore, option A is true. Let order of G is 25, which can be written as 5 square, implies G is an abelian group. Therefore, option B is also true. Let order of G is 55, which can be written as 5 into 11 with 5 less than 11, and 5 divides 11 minus 1, implies G is isomorphic to either Z55 or a non-abelian group of order 55. Therefore, option C may or may not be true. Hence, options A and B are true. Question number 4. This question was asked in NBHM PhD exam in 2007. Let G be a group of order n. Which of the following condition imply that G is abelian? Option A, n equal to 15. Option B, n equal to 21. Option C, n equal to 36. Option A is true. For more detail, see question number 3. If order of G is 21, which can be written as 3 into 7 with 3 less than 7, and 3 divides 7 minus 1, implies G is isomorphic to either Z21 or a non-abelian group of order 21. Therefore, option B may or may not be true. We also know that a group of order 36 is not an abelian group, implies option C may or may not be true. Hence, option A is true. Question number 5. This question was asked in NBHM PhD exam in 2011. How many non-isomorphic group of order 15 are there? Order of G is 15, which can be written as 3 into 5 with 3 less than 5, and 3 does not divide 5 minus 1, implies G is isomorphic to Z15, that is, there exists a unique non-isomorphic group of order 15. Hence, number of non-isomorphic group of order 15 is 1. Question number 6. This question was asked in NBHM PhD exam in 2015. Which of the following statements are true? Option A, every group of order 51 is cyclic. Option B, every group of order 151 is cyclic. Option C, every group of order 505 is cyclic. Let order of G is 51, which can be written as 3 into 17 with 3 less than 17, and 3 does not divide 17 minus 1, implies G is isomorphic to Z51, which is a cyclic group, implies option A is true. Let order of G is 151, which is a prime number, implies G is a cyclic group, implies option B is true. Let order of G is 505, which can be written as 5 into 101 with 5 less than 101, and 5 divides 101 minus 1, implies G is isomorphic to either Z 505 and a non-abelian group of order 505. Therefore, option C may or may not be true. Hence, options A and B are true. Question number 7. This question was asked in CSIR NET exam in June 2014. The total number of non-isomorphic group of order 122 is option 1 2, option 2 1, option 3 61, option 4 4. Let order of G is 122, which can be written as 2 into 61 with 2 less than 61, and 2 divides 61 minus 1, implies G is isomorphic to Z 122 and D 61. That is, there exist two non-isomorphic group of order 122. Hence, option 1 is true. Question number 8. This question was asked in CSIR NET exam in December 2014. Let G be a non-abelian group, then its order can be option 125, option 2 55, option 3 125, option 4 35. Since G be a non-abelian group. Now, order of G is 25, which can be written as 5 square, implies G is an abelian group. Therefore, option 1 is not true. Next, if order of G is 55, which can be written as 5 into 11 with 5 less than 11, and 5 divides 11 minus 1, implies G is isomorphic to Z55 or a non-abelian group of order 55. Therefore, option 2 can be true. Next, if order of G is 125, which can be written as 5 cube, implies there exists a non-abelian group of order 5 cube. Therefore, option 3 can be true. If order of G is 35, which can be written as 5 into 7 with 5 less than 7, and 5 does not divide 7 minus 1, implies G is isomorphic to Z35, which is a cyclic group, implies an abelian group. Therefore, option 4 is not true. Hence, option 2 and 3 can be true. Question number 9. This question was asked in GATE exam in 2014. The number of non-isomorphic group of order 10 is, the order of G is 10, which can be written as 2 into 5 with 2 less than 5, and 2 divides 5 minus 1, implies G is isomorphic to either Z10 or D5. That is, there are two non-isomorphic group of order 10. Hence, the number of non-isomorphic groups of order 10 is 2. Next is number of non-isomorphic abelian groups of order n, or number of abelian groups order n up to isomorphism. If order of G is n, which can be written as p1 to the power a1, p2 to the power a2 up to pn to the power an, then the number of non-isomorphic abelian group is p of a1, p of a2 up to p of an, where pi is the prime number and p of ai is the partition of the number ai. Question number 10. This question was asked in NBHM MSc exam in 2005. How many abelian groups of order 8 are there up to isomorphism? Order of G is 8, which can be written as 2 cube. Then the number of abelian groups of order 8 up to isomorphism is P of 3, means partition of 3, which is equal to 3, and the partitions are 1 plus 1 plus 1, 2 plus 1 and 3. Hence the number of abelian group of order 8 up to isomorphism are 3. Question number 11. This question was asked in CSIR NET exam in June 2015. Up to isomorphism, the number of abelian group of order 108 is option 1 12, option 2 9, option 3 6, option 4 5. The order of G is 108, which can be written as 2 square into 3 cube. Then the number of abelian groups of order 108 up to isomorphism is partition of 2 into partition of 3, and the partition of 2 are 1 plus 1 and 2, and partition of 3 are 1 plus 1 plus 1, 2 plus 1 and 3, which is equal to 2 into 3, which is equal to 6. Hence, number of abelian group of order 108 up to isomorphism is 6. Therefore, option 3 is right. Thank you very much for watching my video. If you like the content, please do like, share and subscribe my channel. If you have any query, comment me. Thank you very much.